Okay, so last time I mentioned, I gave you two examples. One of them we finished, the second one we did not. So the first example we said, suppose you have a magnetic field into the board, right? Here is a magnetic field into the board. So there is magnetic field everywhere in here. It's into the board. Okay? You take a rod of a certain length and you drag it this way with some velocity v. Right? Now this rod consists of F, right? Mainly, as far as charges are concerned, electrons, protons. Okay? So pluses and minuses. So what happens to it is the motion is this way. So positive charges, every single piece of the rod is moving to the right. The magnetic field is in. So the cross product, V cross B, V is this way, B is this way. So V cross B will be this way. So positive charges will move this way, and negatives will move this way. So this end of the rod will be plus, and this end of the rod will be minus. Will be minus. Now they will continue to move until they had enough. Until these pluses, they will set their own electric field down this way to oppose any positive charge that might come up. And in that case, at equilibrium, you got the force from the electric field, which is the charge times the electric field, equals to the force from the magnetic field, which is the charge times the speed times the magnetic field. There is sine theta, but it's everything is 90 degrees. So that's what we have. And so you have the electric field is just the magnetic field times the speed. Times the speed here. Right? So that we did that much. Next we said, if the length of the rod is L, what's the potential difference between the plus and the minus? It was the delta. Go ahead. It was, yes, it was, you integrate this with respect to the y-axis, but this only depends, these are two constants, so it would just be LV, it would be V times the length, so B times L times V, right? That was the potential difference. Okay. Next, we started the following problem. We said, okay, if you have full charge of pluses here, minuses here, these pluses are ready to go, right? They're ready to move, but they reach the edge, they can't just jump off. If you provide them with a path, they will move. And that's the next topic that I started, but I didn't quite finish. So here is the next one. So we will take advantage of our setup. So here is the magnetic field. Again, I can only draw a few X's this way. Otherwise, it just gets too messy. So I'll just draw this guy. But it's understood that there is a magnetic field into the board, right? Everywhere here. Okay. So here's the setup. We're still going to have our rod this way. We're still going to drag our rod with a velocity v, but then we'll just get this situation. So we want to provide our pluses a path to go around. So I'm going to put a resistor here, and the charges can go like this. And this is like a rail. So the rod can slide on top of the rail. Does that make sense? Okay. Oh, here's the rod. So the rod can slide and it's touching a rail like this. So it's sliding on top of the rail. Okay. With some velocity. And so there is a resistor here. And the question is, in what direction will the current flow? Well, we said pluses will get to here. And what do they want to do eventually when they get here? The magnetic field is pushing them, so they will go this way. So you would have a current in the circuit circulating like that. Now, since there is a potential difference between here and here, that potential difference is equal to V times L times V. There will be a current in the circuit. And it's like you have a battery that provides a potential difference of a certain voltage and there is a resistor here. So what would the current be? Well, we know from Ohm's law, V equals to IR, right? So delta V equals to IR, and therefore the current I will equal to the potential difference, which is VLV, V over I. The length from here to here is now. So that's what we did last time. Okay. So far, so good, right? Then I said, what is the work done by the magnetic field? And then what's the work done by the force that is pulling? Okay? What is the work done by the magnetic field, and what's the work done by the pulling force? So consider let's do the magnetic, the work done by the magnetic field. So suppose you have a plus charge here, and the question is, how much force, what's the force on that charge due to the magnetic field? What is the force on this charge Q due to the magnetic field? Well, I know that, first of all, this charge Q will have a velocity of what? This charge Q is moving in what direction? Let's think about it. Yep, it's being dragged with a velocity v to the right, but there is also a current, so it's also sliding up. So it's moving in this kind of diagonal direction. And let's call this I hat direction, J hat direction, and the K hat direction will be out of the board. So this charge will have a velocity this, let me call it V total velocity, will equal to this. The velocity that it already has to the right, due to the rod moving to the right, which is V times I hat, right? V times I hat, it's moving in the right direction. Plus the velocity it has due to the magnetic force pushing it upward, so there is a current. So it has a velocity U, we can just name it U. Okay. So plus this U J hat, right? It's in the J hat direction. Okay. The magnetic field is in the into the board, right? Is into the board. What is that direction? Minus K hat. So minus K hat, and it has a magnitude B. Okay. Let's find the force. The magnetic force, the force due to the magnetic field, will be the charge times the velocity, but you need to account for both velocities, the x and y components, so the total velocity. Total velocity, cross product with the magnetic field. Cross product with the magnetic field. Any questions on this? So, can someone summarize again, why do I have two velocities, one in the x direction, one in the y direction? Where does the v velocity, the I hat direction come from?
From the
Because the rod being dragged this way. And where does the u come from? Because the charges are, due to the current, they're moving down. Okay, good. And the magnetic field is into the board, so minus something times k hat. So let's take the cross product. So first, you have to do the cross product here. What is I hat crossed with k hat, or with negative k hat? So here's I hat, here's minus k hat, and you take their cross product in one direction. I hat minus k hat. I see a thumb up. So in what direction this is? J hat. So this VI hat crossed with minus VK hat will give me this. So you have the Q here, will give me J hat, and then VB. Okay, VB. Let's look at this one. The J hat crossed with minus K hat. J hat is up, minus K hat is in. So in what direction is the cross product? You got a vector this way, a vector this way. I want to take the cross product from this vector crossed with this vector. Yes, curve your fingers from this vector toward this vector. And you get, yes, minus I hat, and that's U and V. You can factor V out. Now, I want to find out what the work done by the magnetic field is, right? That's why I've calculated finding the magnetic force. Again, what should the work done by the magnetic field be? It should be 0. So let's show that it is 0. So dW, dW of the magnetic field, a small amount of work of the magnetic field will equal to this. The magnetic force dotted with the displacement, dr, right? So the magnetic force is this. It's Q B Vj hat minus U I hat dot product with dr. In what direction is the displacement of a charge? It's to the right and up. So it's a displacement of an amount dx in the I hat direction plus an amount dy in the j hat direction. Yeah, that's the displacement. Let's take the dot product. Well, j hat dot I hat is 0, right? I hat dot I hat is 1. So you will get this. You will have a dW will be QB times. So again, j hat dot I hat is 0. And then j hat dot j hat is 1. So j hat dot j hat is 1. So I got just V times dy. So I get V times dy minus I hat dot I hat is 1. So I got minus U dx. And that's it. And then this I hat with j hat is 0. Okay. Now, what is U? U is dy dt. Right? U is the velocity in the y direction. So it's dy dt. So you get QB and then V dy minus U, which is dy dt dx. So this is QB V dy minus, let me divide the dx by the dt. What's dx dt? That's V. So you end up with V dy. So you get V dy. And so this ends up being what? Yeah. Alright, good. So the magnetic field does not do any work. So 0. So who's doing the work?
The electric field.
Force pulling.
The force pulling. Let's say it's the person, me, you. Somebody's pulling. So how much work do they do? Okay. So since this thing is sliding to the right at constant velocity, right? The rod is being pulled to the right at constant velocity. It means the force provided this way has to equal to the magnetic force that is backward, right? You see the magnetic force has 2 components, right? One of them is QB in the j hat, and then there is this one in the I hat direction, minus I hat. So that's the component. This component is trying to drag you back, but you have to pull it this way. So you have to provide this an equal amount of this. So let's see what the pulling force provides. So dF pull, well, it will be in the x direction, no reason to put the vector sign. So dF pull would be what? So suppose I'm pulling a charge, a small amount of charge, dq. Let's work with the dq first. So you would get a dq. I'm looking at this, dq, and then u times b. And then u times b. dt, so I get dq dy dt times b. Now divide dq dt. Divide the dq by the dt. What's dq dt? Current, right? That's the current. That's I. So you get I times b times dy. That's the small amount of force of pull. Now to get the total on the entire rod, you have to integrate this along the rod. The rod extends from y equal to 0 to y equal to L, right? The rod is length L. So you will just end up multiplying by L. So the pulling force then in total, at pull, will equal to I times V times L. That's the force with which you're pulling. Okay? Yeah.
For the velocity, what do you have U again, just like by itself instead of just like V?
Yeah. So your pole is to the right. The magnetic force is given this component for J hat. That causes the current, the charges to move up.
Okay.
But you're trying to pull the rod this way.
Oh, okay.
So the magnetic force is providing the force to the left. So you have to apply a force to the right. You cancel that.
Okay.
Yeah. And it has to be equal to it because we're assuming we're not accelerating. We're just moving at constant velocity. So the net force has to be 0.
Okay, thank you.
So that's the pull. So how much work are we doing? Well, let's see. Let's put dW pull. dW pull is equal to F pull dx, right? If you pull it an amount dx to the right, that's how much work to do, right? F dot dr, but dr in this case is just dx for the rod, it's moving to the right. So, let me do this. dW pull dt. What is the work done per unit of time? Power. Yes. So power is the amount of work that you do per unit of time. So it's power. So the power of the pull will equal to F pull times dx dt. F pull times dx dt. But dx dt is V, right? Dx dt is V. So the power of the pull is equal to the pulling force is IBL. Pulling force is IBL, and then this is V. So you get I B L V. Okay? IBLV. But what's the current? Way up there. I know it's a long problem, but it's an important problem for demonstrating this concept. What's the current? Can someone see it?
BLV over R?
Yeah, it's BLV over R. That's the current. So the current is BLV over R. So you got BLV times BLV over R. So what does that end up being? The power of the pull will end up being what? I, which is BLV over R, times BLV over R. So it's B squared, L squared, V squared over R, right? So it ends up being B squared, L squared, V squared over R. That's the power of the pull. That's how much energy you're spending per unit of time. So how much energy does the resistor consume per unit of time?
Equal to.
It has to equal to it. Well, let's verify it. The power consumed by the resistor, I put PR, power consumed by the resistor is I squared times the resistance, right? You know this from circuits. So I squared R, so the power of the resistor, I squared. Well, square the I is BLV over R, so when you square it, you get B squared, L squared, V squared over R squared, but you're multiplying by R, so you just end up with an R at the bottom, but everything else is the same, so it's also V squared L squared V squared over R. Okay. We'll do a quick example. This one. So So here's an example. Suppose the magnetic field is into the board. You have a resistor here. And you're pulling with a velocity v. There is a magnetic field N. So I'm not going to draw a bunch of them, but there is a magnetic field into the board. And this length, the length from here to here is L equal to 0.1 meters. That's the length. Uh, 0.1 meters, yeah. Suppose the magnetic field V is 0.1 Tesla. That's the magnetic field, 0.1 Tesla. And you have a light bulb here, or a resistor, and the resistor experiences a potential difference of 3 volts, and it consumes a power of 1.5 watts, 1.5 watts. That's the power consumed by the resistor. The questions are, find the speed and find the pulling force. So find V and let's look at the resistor. The voltage across the resistor, this is the power in the resistor. So I know that for the resistor, the power is V squared over R, right? V squared over R. And it's also equal to IV, current times the voltage. Current times the voltage across the resistor, right? So I can find the current. I know the power, I know the voltage, I can find the current. So why not? So I get the current equal to the power over the voltage. Power is 1.5, the voltage is 3, so I get what? Half, right? 0.5. So 0.5 amps. Okay. Sounds good. Next, I can also find the resistance of this resistor, if I want. So why not find the resistance? So the resistance, I can do V equals to IR. So R would be the voltage divided by I. The voltage is 3, I is 0.5, so I get 6. 6 ohms. The resistance is 6 ohms. I think we've found everything we need to find about the resistance. We know the power it consumes, we know the voltage across it, we know the current through it, and we know its own resistance. So now let's see if we can find the velocity. Well, anything related to the velocity. Well, here it is. That's the power consumed, right, by the resistor. It's B squared, L squared, V squared over R. So we can use this one to find the speed, right? So we can just use this. We'll say the power in the resistor would be V squared, L squared, V squared over R. So V would be B times L times the square root of the power times R. We multiply, take the square root. B is 0.1, L is 0.1. Actually, I made a mistake, right? Yeah, I made a mistake. What is it? Yeah, so it's PR divided by B squared L squared, so this should be on the bottom. Should be on the bottom, let me rewrite it. So PR square root divided by PL. Yeah. Otherwise it would be moving super slow. Yeah.
You should also use the change in potential equals BLV. Right above here.
Yeah, you can also do that. So, there are different approaches. I think every time I solved this problem, I did it a different way. So, so let's do, since we wrote this one, yeah. So the power is 1.5, right? 1.5. The resistance is 6. So that gives us a 9, and the square root of 9 is 3. That's a nice number. And then these are 0.1 times 0.1. And so you get 300, right? Meters per second. Three. Okay. How about the pulling force? It's what? IBL, right? You can use this one. The pulling force is IBL. So that pull. We found the current a while ago was half an amp, 0.5, 0.1 for B, 0.1 for L, and you get 0.005. So you see here, you can have a light bulb, and you can light the light bulb using your just muscles. You need a magnetic field, but you can just pull it, and that's what a generator does. Just a human muscle generator, or some, you know, somebody has to pull this thing. I mean, obviously it's not very practical. You cannot pull it you cannot make the rails, you know, 100 miles long and keep running. So there are better ways, but it's a good starting point, right? Yeah. Good starting point. Now, even though the magnetic field is doing zero work, it's still needed. Without the magnetic field, you can pull it, but who is going to push the individual charges up? Nobody. It's the magnetic force that makes them push up. Sure, it does positive work on the way up, but it does negative work this way, because you're dragging them in this direction, the magnetic force is opposing it. So it does a total of zero work, but it's still needed, because you cannot push the individual charges by yourself. Okay. Now we're going to go to another topic. Here's that other topic. You see here, I have to make the rod move, right? I have to make the rod move. What if it's not the rod that moves, right? I mean, you can be moving away from me, or maybe I'm moving away from you. We're relative to each other. So maybe if I make the magnet move, do I get the same thing? And the answer turns out, yes, you get the same thing. But how do we explain that? You can't explain it using QVB, the magnetic force, right? QVB in this case, because the charges were moving, there was a magnetic force on them. But in the case if the magnetic field is moving, from our perspective, the charges are not moving. It's the magnetic field that's moving. So, but yet you end up with the same thing. And that's Faraday's law. That is called Faraday's law. It says you can get the same thing by having the magnetic field moving. Now, if it's the magnetic field moving, and you get the same thing, you get the same current, now who is pushing the charges? Right? You're just pulling them. Actually, you're not. In this case, let's say you're not pulling them. Somebody just changing the magnetic field somehow. Pulling the magnet. So, the charges can move using two forces. One of them is the magnetic force, right? How about what's the other force? Electric force. Electric force. So what it says basically is a change in magnetic field will induce
An
an
electric
electric field. An electric field that's not due to static, electrostatic charges, but due to a new origin, due to a change in magnetic field. So that is the next topic. Okay. So to do that, we're going to talk about magnetic flux, and very similar way, very similar definition to the electric flux. And I had this demonstration that we will hopefully understand by the end of the lecture today. I have a copper pipe, so it's not magnetic. It's not. But I have two things here. They look the same way, but one of them is a magnet. The other one is not. This one is a magnet. This one is not a magnet. This one is just a piece of metal. Okay. So this is the magnet. This one is the piece of metal. And we're going to run them through this pipe. All right, so ready? So this one I'm going to just let go. Nothing, right? It just fell. Just fell. So let's look at the magnet. Really, really slow. And you can try this with, you can just go to, in fact I'm going to, I asked for a bigger copper pipe here, we didn't have it. Maybe we should go to Home Depot and get one. And you can try it on your own. So you have a magnet, so here's the magnet, and I let go. Takes a while. You put just a piece of metal, just falls due to gravity. So what's going on? Somebody is opposing it. And that's the induced, basically magnetic field in here. So, by the way, anybody wants to try? You can wait. Maybe two people want to try it. Come on. Yeah. Keep going. Try it first. I don't know which one is which. That's the magnet. You have this one. Yeah, nothing. Yeah. So, yeah, thank you. It's a really interesting one, and it's a demo anybody can do. All you need is a magnet and a pipe. As long as the magnet can fit through the pipe, it's fine. It will work. Okay. So the next topic is the magnetic flux, and that will explain this. That's what we're trying to do. Okay. So magnetic flux. So remember flux, or electric flux, the electric field going through an area, right? Passing through some area. That was flux. It's a measure of how much of something goes through. So how did we define the electric flux? Okay. It was related to Q, but in terms of just the field and the area. EDA, yeah, the electric field times the area, basically. Yeah. So the magnetic flux is the same thing. So suppose I have a magnetic field in this direction. Here's the magnetic field, right? And I have a loop, and so let's say my loop is this one, right? And it has an area A. Is this the optimal magnetic field going through it, or not? Yeah, it's facing the magnetic field wants to go this way, and my loop is facing it, right? And I should have had my cup of something. So let's say the magnetic field is coming down from the top, coming down from the ceiling. The magnetic field is downward. If the loop is like this is optimal, right? This is the loop, the magnetic field loop. This is not good, right? How much magnetic field will pass through this loop? It will just, nothing goes through it if it's just falling. So in this case, the area points this way and the magnetic field points down. In this case, the area points parallel or anti-parallel to the magnetic field, so you get maximum flux passing through. So it will be the way we define it. See, it's hard here to draw a. Let's say my loop is this way. So the area of my loop is pointing in this direction. The magnetic field is pointing in this direction, right? This is dA. And they make an angle theta. And so the flux, the magnetic flux would be the integral of B dot dA. If the magnetic field is constant and the area is constant, so they don't change their orientations and magnitudes, then this boils down to the following. If the magnetic field is constant, right, and it's uniform and so on, and the area is not rotating, then this ends up being the magnetic field times the area times the cosine of theta. If the magnetic field is not uniform, then you will actually have to do an integral, and we're going to do one. We're going to do an integral. Okay, to calculate the flux. So here's the first. Oh, by the way, units of magnetic flux are. Can you guess the units? Tesla times
Meter. Meter squared.
Meter squared.
meter squared. Yeah. So the units are Tesla times square meters, right? And this is called the Weber. Just another measure. WB. So it's Tesla times meters squared. So just in case you see. Okay. So let's do a question for a non-uniform field to see how we can calculate the magnetic flux. Okay. So here is the example. Suppose I have a current in this direction. I think the current is, let's say, 2 amperes, not 1 ampere. Let's say the current is 1 ampere, okay? So in what direction is the magnetic field on this side? And then in what direction is the magnetic field on this side? So let's start with this side. Coming out? Yes. So okay. So put your thumb with the current, and the magnetic field will be looping around it. So here it comes out, here it goes in, right? Yes. So the magnetic field is coming out here, and it's going in. And again, even though I drew just a few, anywhere here, the magnetic field is out. Anywhere here, even way over there, the magnetic field is in.